Okay, welcome back to Real Analysis. In section 8.3, we're going to develop some properties of the definite integral. Let me remind you, in 8.2, we proved the existence of it. That is, we proved that if you have a continuous function on a closed interval, there's this number. It's called the definite integral of the function over that interval. That number exists and is basically within any positive distance epsilon away from a Riemann sum over that interval, provided that the norm of that Riemann sum is small enough. Right. So in this section, I want to develop some properties of the integral. We're going to continue to assume that f is continuous. Later, we'll relax that a little bit. You can compute and define definite integrals for functions that aren't necessarily continuous. But here, we're going to continue to assume f is continuous. So in particular, the definite integral for f, any continuous function, is defined. We don't have to worry about defining it. So when we look at these properties below, equations, if you like, that the integral satisfies, we don't have to worry about proving the existence of the integral in the equations. We know they exist because the functions involved are continuous. We have to focus our attention on showing that the equations that we're talking about hold. Okay? So to that end, we're going to kind of use the following device. When we defined definite integrals, we said that this number satisfies some condition for tagged partitions. So I'm going to use a specific kind of family of tagged partitions. If you give me a natural number n, then I'm going to denote by p sub n a partition. It's got some number of points in it. It depends on n, so I'm calling the number of points m of n. And it's a partition of the interval from a to b, and I want its norm to be less than 1 over n. So if you like, I can always choose such a partition. If you're wondering how to do that, well, given n, I have a and b, I could choose a number m of n so large that b minus a over it is less than this 1 over n. How do I do that? Well, I would just pick m of n bigger than n times b minus a. I'm given n, I'm given b, I'm given a, and the Archimedean principle says I could always pick a natural number like that. So if you give me some natural number n, I'd pick m bigger than n times b minus a, and then I can just choose, say, the left endpoints. I'll let x sub k be a plus k times that width, b minus a over mn, for k equal to 0 to m minus n, and that gives me a partition. All right, so I can always pick a partition p sub n whose norm, the norm here of the partition that I've constructed, is precisely this number b minus a over mn, m of n, and that norm is less than 1 over n by construction. And for that matter, I'll always tag that partition. Let's remember our tags were these c sub k's. I'll just choose them to be the left endpoints. Okay, so of each subinterval, I just pick c sub k to be the left endpoint of that subinterval, and that always gives me a tagged partition whose Riemann sum I will denote the same way we did before, S of f, and this tagged partition p sub n. So what do? I plug the left endpoints into my function, I multiply it by the width of the corresponding subinterval, and I add those things up. All right, so I always have such a partition, and I claim that that's a number. This Riemann sum is a number that depends on n. So it gives me a sequence, if you like, of Riemann sums. And I claim that the limit of that sequence is the definite integral. So I'm just going to call this a lemma and try to prove it to you real quickly here. So I've got a sequence. The nth term in my sequence is the Riemann sum associated with the nth partition in this family of partitions. So to prove that that sequence converges to this number, this definite integral, I'm just going to use the definition of sequence convergence from back in chapter 2. So give me an epsilon. I'll use Cauchy's theorem. F is a continuous function on this closed interval, so I know there's some delta, so that if you take any tagged partition, say p dot, the Riemann sum of that tagged partition differs from the definite integral by less than epsilon, provided that the norm of the tagged partition is less than delta. All right, so I've got this delta. Well, then pick a natural number so big that its reciprocal is less than delta. So if little n is bigger than that natural number, well, then 1 over n is less than delta. So in my family of tagged partitions above, their norms are less than delta. So the corresponding Riemann sum differs from the definite integral by less than epsilon. So what have we done at the end of the day? We've shown that given an epsilon, we can find a capital N so that if little n is greater than or equal to it, my nth sequence term minus this definite integral is less than epsilon in absolute value. Well, that is precisely the definition of this sequence converging to that number, that definite integral. All right. So I'll use this lemma repeatedly below. When I want to prove something about a definite integral, I'm going to prove it about the partial sums for this family. Not partial sums, sorry, that's my calculus brain taking over. I'm going to prove it about the Riemann sums for this family of partitions that we wrote down. Okay, let me illustrate. First property that we're going to talk about is a familiar property from calculus. The author's calling it the additive property. So if you take some continuous function on an interval from A to C, maybe I can just sort of sketch a little picture of an interval over here. So f is continuous on this interval from A to C. Okay, so it's got an integral. The definite integral of f exists. And you pick some number b somewhere strictly between A and C. So maybe that number b lives right there. So then we have two intervals. I've got the interval from A to B and the integral from B to C. F is continuous on them both. So that the integral of f exists on them both. And this property is saying that if you take the integral over the first half, A to B, and you add the integral over the second half, B to C, you'll get the integral over the entire interval. All right, so it's this so-called additive property of integrals. You can split an integral at any point between A and C. Okay, so how to prove that? Well, let's take those tagged partitions we constructed above, those families. So P sub n dot is a partition for every n. We're partitioning the interval from A to C. Its norm is less than 1 over n, and we're choosing the tags as the left endpoints. But we can always arrange if we want to. We'd have to change the way we defined those x's up there, but we can always arrange that this number b is some number between A and C, we can always insert it as one of the partition points, okay? If you like, you can construct P sub n as above, and then just sort of modify P sub n by sticking B in there, always choosing it to be one of the partition points, okay? I kind of got a picture of that drawn down here, so let me just sort of reveal it. So then for any n, P sub n kind of splits into two partitions. I'm going to call them P sub n prime and P sub n double prime. They're both still tagged because I'm using the left endpoints. And because P sub n's norm is less than 1 over n, well, then both of those partitions will have norm less than 1 over n. So look at the picture down here. I've got the interval from A to C, and I've partitioned it into this P sub n, and I'm picking the left endpoints as the tags. So what I'm saying is, well, since I'm always assuming that B is one of the partition points, then some of those subintervals are going to be in the interval from A to B, and I've highlighted in red here the tags that I'll use. They're always the left endpoints. So the red tags are the tags for Pn prime. And then I'm highlighting in blue the left endpoints starting for the subintervals that are in the interval from B to C, right? So those are the tags for Pn double prime. And the picture is supposed to show us that those tags together, union together, to give me all the left endpoint tags for Pn. All right, so if you believe that, then you believe that the Riemann sum for that partition Pn can be split into two sums, the Riemann sum over the red tagged partition for Pn prime, plus the Riemann sum for the blue tagged partition, Pn double prime. Right, you just split the sum. In my notation here, this first sum, the Riemann sum for Pn prime, you would sum the index from 1 to j, right? So we're using the left endpoints. And then in the second one, you'd sum the index from j plus 1 up to m of n. Okay, so I've got my sequence terms written as a sum of two other sequences. F is continuous, so each one of these Riemann sums converges to the corresponding definite integral. So if we just take the limit as n goes to infinity, well, over the entire interval A to C, the Riemann sums of f over the Pn, the tagged partition Pn, that converges to the integral from A to C. This first term on the right-hand side is going to converge to the integral from A to B because Pn prime is just the partition for up to B. And the second one is going to converge to the integral from B to C. All right, so there's kind of that's a proof of this additive property of integrals. Nice. We'll use that additive property in the subsequent lecture to prove a little theorem called the fundamental theorem of calculus. So it's going to be an important tool for us. Here for the linear algebra or abstract algebra people, the definite integral is linear in the sense that the definite integral of a linear combination of the functions f and g is a linear combination of the definite integrals. So, or as stated here, if f and g are both continuous on a to b, then if you take any two real numbers, that equation holds. Right? So the integral of the sum is the sum of the integrals, and you can pull constants through integrals, as calculus students say. Here, I'm just going to kind of highlight the proof. It's a sketch of the proof because it's really the same ideas, and it just kind of makes the video long to kind of write out all these things in careful sentences. But I hope you get the gist of it. That so under all of these conditions, using the notation above with these special tagged partitions, Pn dot, well, the Riemann sum of Pn dot as n goes to infinity would converge to the integral of f. But the Riemann sum for G over that tagged partition as n goes to infinity converges to the Riemann sum for G. Okay, you can kind of do the arithmetic, but the Riemann sum for this linear combination alpha f plus beta g is just going to split into the Riemann sum for f times alpha and the Riemann sum for g times beta. Right? That's just because you can regroup the terms in the sum. Alpha and beta are in every term. You can factor them out. So that's just by properties of summation. Okay, well, then by limits of sequence laws, right, we have these two sequences individually that converge to these integrals. Their sum then converges to the sum of those integrals. Okay, also constant multiples converge to constant multiples. So this Riemann sum for the linear combination alpha f plus beta g, it converges to the linear combination of those definite integrals. But alpha f plus beta g is a continuous function on a to b. So our lemma at the beginning of this lecture says that the Riemann sums for alpha f plus beta g converges to the integral of alpha f plus beta g over the integral. Well, so this sequence only has one limit, right? So the sequence is converging to the sum of these integrals. The sequence is converging to the integral of that sum. So those two things have to be equal to each other by a uniqueness of sequence limits. Cool. So there's the linearity of the definite integral. Nice. A couple more. I'm not going to walk through the proofs of it. The monotone property. So it's kind of an order preserving property. If your two continuous functions satisfy, say, one of them is dominated by the other. So f is less than or equal to g for all x in the interval. Well, then the integral for f will be less than or equal to the integral for g. So I'm going to kind of leave it to you to construct a proof of that using these partitions. You can just sort of argue that it would be true for any Riemann sums with those tagged partitions Pn. And then we know that like sequences that are dominated like this, the inequality rather is preserved when you take limits of sequences. And so that's how you'll prove that. So I'm going to leave that one to you. Not write out the proof here. I am going to mention this absolute value property of integrals, 8.7. It just follows from 8.6. The author has it kind of written in two forms here. So what's he saying? He's saying if you take a continuous function on this interval, the opposite of the absolute value, which is also continuous, right? The absolute value of f is continuous when f is no more than the integral of f, which is no more than the integral of the absolute values. Or just using that idea that if you take some number, let me not use a and b here because I want to not confuse the notation. Remember that a is between a number and its opposite if and only if its absolute value is less than or equal to that number, for a positive number beta. So if you use that idea, you can rewrite that thing just like this, okay? And that actually, we can kind of scratch out a proof. It follows just from 8.6, because for any x in the interval, certainly a number f of x is greater than or equal to the negative of its absolute value and less than or equal to its absolute value. So then you just apply 8.6 twice. You apply 8.6 to these things, and you would get the integral of the negative of the absolute value of x is less than or equal to the integral of f. Apply it to the second ones to get the integral of f is less than or equal to the integral of the absolute value. And that's exactly what this thing says. So two applications of 8.6 gives it, and then you can just rewrite that in this form. Nice. Okay, I'm going to try to keep this video shorter because the last one was pretty long. We can use it as kind of a catch up if we need to. I just want to kind of compare, and I need to zoom out a little bit so you can see them. But remember when you proved in your homework this kind of what I'm calling the generalized triangle inequality, that if you take a bunch of real numbers, I didn't even quantify them here, but if x1 to xn are real numbers, then the absolute value of the sum of them is never any more than the sum of their absolute values. So the triangle inequality is just the case where k or n is equal to 2 rather. So this is why I'm calling this the generalized triangle inequality. Just compare that to this statement up here. In some sense, this theorem that the author is calling the absolute property of integrals, it's really just kind of like a triangle inequality for the integral, for the definite integral, saying that the integral of the functions, the absolute value of the integral of the function is never any more than the integral of the absolute values. So if you just kind of replace the summation sign in the generalized triangle inequality with the integral sign up above, replacing f of x with x and so on, then it's in some sense kind of the same result. Okay, thanks for listening.